The topic of my presentation are LPE grown on thermoluminescent detectors based on doped garnets and perovskites. First, I would like to talk about background, materials and methods, and the first part is about composite detectors using garnets, and the second part is composite thermoluminescent detectors using perovskites. The simultaneous registration of the different components of mixed ionizing fluxes strongly demands the development of the new types of composite detectors with the ability to separate the signals coming under alpha, beta particles, and gamma quanta irradiation. Recently, we have shown that the epitaxial structures based on cerium-3+, plus ruthenium-3+, and scandium-3+ doped single crystalline films SCF and single crystal SC of garnet compounds prepared using liquid phase epitaxy LPE. Grown method can be successfully applied for this task. The application of composite scintillators presupposed that active mode of in situ registration of incoming ionizing fluxes. Mainly such a mode of registration is not always possible, especially in the case of low doses of radiation and the long-time radiation exposure, or due to limitation of analysis of the liquid and gas radioactive materials or high-doses sources. The above-mentioned problems demand consideration of other approaches for producing the composite detectors of ionizing radiation. Nowadays, we consider the new possibility for simultaneous registration of the different components of mixed ionizing fluxes using differences between the TL glow curves coming from the film and substrate parts of a composite detector. Thermoluminescent detectors were grown using the LPE method from the melt solution based on the PBO flux. For characterization of the luminescent properties of the single crystal film and single crystal parts of composite detector, under high energy excitation, the cathodoluminescent spectra of SC and SCF parts of composite detector were measured using SEM-GEL JSM 820 electron microscope. Additional equipment with stellar net spectrometer working in 1100 nanometers range. For TL measurements, we use the result TL reader under alpha and beta particles excitation by 241 americium and 90 strand sources respectively. The first part is about garnets. The goals are creation of composite thermoluminescent detectors based on the film crystal epitaxial structures of garnet compounds for the simultaneous registration of mixed ionizing fluxes containing alpha and beta particles. And the second goal is improved separation of TL glow curves of single crystal films and substrates in comparison with the prototype of such composite detector based on lutetium aluminium garnet doped by cerium epitaxial structure using cation engineering of single crystal film content, and we use for this part gadolinium doped. The TL glow curves of lutetium aluminium garnet doped by cerium single crystal film and yttrium aluminium garnet doped by cerium single crystal and yttrium aluminium garnet with cerium single crystal film on lutetium aluminium garnet doped by cerium single crystal epitaxial structure after irradiation by alpha and beta particles show differences. Namely, for the first structure, the main peak are observed at 325 and 215 after irradiation alpha and beta particles, respectively. When the second epitaxial structure, the corresponding peaks are located at 180 Celsius degree and 345 Celsius degree, respectively. As is mentioned above, alpha particles of 241 americium source with a typical pathway in the lutetium aluminium garnet and yttrium aluminium garnet hosts of 10 to 12 micrometers are fully stopped in single crystal film parts of a composite detector with a thickness of several 10 microns, when beta particles of 90 strontium source with an average energy of 1.1 megaelectronvolts can penetrate in the whole 1.3 millimeter thick yttrium aluminium garnet and 0.8 millimeters lutetium aluminium garnet single crystal substrate. Free for the TL signals from single crystal films and single crystal parts, the both composite detector under study corresponding mainly for the registration of alpha particles and beta particles respectively. In our opinion, the most suitable ranges for registration of differences in the TL glow curves for these epitaxial structures, composite detectors, lies between 150 and 400 Celsius degree, where the largest differences between the respective TL peaks is observed for single crystal film and single crystal part of composite detector. The creation of novel types of composite TL detectors based on lutetium aluminium garnet doped by gadolinium epitaxial structure for simultaneous registration of mixed ionizing fluxes containing alpha and beta particles is reported in the second part of first topic. The detectors consisting of lutetium aluminium garnet doped by gadolinium single crystal film with gadolinium content in the range 0 to 1.5 were fabricated using the liquid phase epitaxy LPE grown method onto yttrium aluminium garnet doped by cerium. The registration of alpha and beta particles by the single crystal film and single crystal components of composite detectors was performed using differences between TL glow curves of these components of composite detectors using delta T parameters. Manville duty feeding influenced the optimal garnet combination for the creation of composite detector is for this epitaxial structure with delta T value above 150 degrees. In field results on lutetium aluminium garnet doped by cerium single crystal film onto YAG with cerium single crystal and YAG with cerium doped single crystal film onto lutetium aluminium garnet with cerium single crystal epitaxial structure after alpha and beta excitation we have observed the significant differences in the position up to 80 Celsius degree and intensivity of the main TL peaks of the glow curves of single crystal film and single crystal components of this epitaxial. The obtained results confirm the assumption that the cation engineering of single crystal film content enables the significant improvement of TL properties of composite detector. Namely, the application of such an approach leads to an increase of the difference between TL glow curves using epitaxial structures doped by gadolinium substrate up to 150 to 215 degrees in comparison with the respective value 80 degrees of the prototype of a composite detector based on lutetium aluminium garnet with cerium and yttrium aluminium garnet with cerium doped epitaxial structures. The second part of my presentation is about perovskite. Material engineering proposed two approaches have been proposed using various types of admixtures without changing the matrix and the differences matrices of scintillators materials done with the same type of activators. The mentioned material hosts possess the different density of effective atomic numbers, heavy gadolinium-based garnet and much lightly yttrium-based perovskites, and for this reason can be applied for the simultaneous registration alpha, beta particles, as well as X-ray gamma quanta in the wide energy ranges. The choice of mentioned dopants in these materials is due to the fact that these ions typically create the hole cerium-3+, and electrons manganium-3+, trapping centers in oxide compounds. For this reason, the TL glow curves in mentioned materials a priori can be different significantly. The first samples is about gadolinium aluminium perovskite. And we see in this table alpha particles absorption with energy 3.5 mega electron volts, absorption of photons with energy 10 kilo electron volts, and energy 60 kilo electron volts. In this part, we observe the different matrices of scintillators materials though with the same type of activators, cerium-3+, using GTAP and YAP. The peak 241 only occurs in the case of beta excitation. Similar in the case with the sample with thickness 35 micrometers. It's worth paying attention of the intensivity in the range 240 to 350 nanometers, which is characteristic for the substrate. And the same situation we see on the last samples with thickness 12 micrometers. Area free from analyzing X-ray is signaled from layer and from the substrate. If we look at the green curves from the layer thickness of 35 micrometers, where the absorbent 97%, can be said that the region 3 and 4 for this sample is actually only a signal from the substrate. We show some dependence and observe intensity decrease with thickness and absorption increase with thickness. In the second part of this topic is using various type of admixtures without changing the matrix, manganium, yttrium, aluminium perovskite. The CL spectra of YAP with manganium single crystal film with manganium concentration are shown in this picture in comparison with YAP with cerium substrate. Cathodominiscent spectra of YAP with manganium single crystal film present the superposition of the luminescence of different valence states of manganium ions. Specifically, the luminescence of manganium-3+ ions in the board band peaked approximately at 650 nanometers. The luminescence of manganium-4+ ions in the octahedral sites of aluminium-3+ cations in the characteristic band peaked at 677 and 712, as well as low-intense luminescence of manganium-2+ ions in the cube octahedral position of yttrium-3+ cation in the band peak at 530, are observed in the cathodominiscent spectra of YAP using manganium-doped single crystal film. We observe similar situation, and we observe peak 213 only occurs in the case of beta excitation, and peak 54 for X-ray excitation. The situation is the same in the next samples with 70 micrometers thickness. And you can see that the curves and the difference is some areas which could mean that the signal from the places come from 90 strontium, 90 yttrium radiation passing through the layer. And the second conclusion are the CL spectra of YAB manganium single crystal film. We're analyzing in the demanding of manganium content. We have found the presence of luminescent manganium 3+, manganium 4+, and manganium 2+ valence states of manganese ionized. The thermoluminescence properties of composite detectors based on the LPE growth GDAP with cerium and YAB with cerium, YAB with manganium and YAB with cerium epitaxial structures were examined under excitation by alpha and beta particles using americium, strontium, and yttrium sources. The registration of alpha and beta particles by the single crystal and single crystal films components of composite detectors, respectively, was performed using differences between TL glow curves of single crystal and substrate. The results show that samples with large ability of X-ray absorbance of films can be considered as a perspective materials for development of thermoluminescent detector. Thank you for your attention.